Hello, everyone. My name is Xiaojun Liu. I come from Jianyuan Nanhu University, Zhejiang, China. Our topic today is BIM indoor path planning, a lightweight approach from complex BIM buildings. There are several parts in our presentation. Let's start with the first one, introduction. With the popularity of navigation tools, especially those of smartphones or other lightweight devices, the application of indoor environmental navigation has received a great deal of attention, particularly for the buildings with complex indoor structures. Their irregular and crowded indoor environment can result in emergencies at a high probability. And one of the main reasons for this serious incidents is that indoor escape and evacuation are not efficiently and timely. For avoiding this situation happening, it's urgent to explore a lightweight indoor path planning method to meet the requirement of the emergency indoor route finding. For the building date, BIM has become the core technology in smart building, and its date has also been regarded as the source code in BIM building information. IFC, as an international mainstream standard from BIM technology, is capable of restoring both geometric and semantic information of building models, as well as their relationships. In this paper, we take IFC as our input data format for the indoor environment analysis. However, its rich information also brings disadvantages. For example, huge volume, high rate of redundancy, and lack of spatial information for data processing in practical application, especially for lightweight indoor path planning. Observing that both environment modeling and path searching is important, we integrate these two together with a lightweight approach, and our main contributions can be summarized as first, a lightweight framework is designed in which all the online computation for a whole building is decreased within no more than 2 local interior spaces. Second, a multi-layered network structure is proposed for indoor environment modeling and a corresponding automatic method for this structure generation. Third, a heuristic optimized A-star algorithm is implemented to speed up the shortest last local path searching, especially for the case of path ends in a narrow corner. As described above, we also give the related work from indoor environment modeling and path searching algorithm. In indoor environment modeling, works for GIS state appears relatively early, yet fewer works for BIM buildings are related with path planning. In addition, cell grid or topological structure is mainly measured for modeling structure. In path searching algorithm, the traditional and intelligent category are classified from a technical principle. In contrast, the last category is more apt to address the path planning with stochastic process, while the other, which we are more interested in, is definitively capable of converging to a shortest path. However, there are still many aspects need to be improved. The first is the efficiency of the whole method. Most of existing methods run on standalone devices, yet lightweight or web-based ones have rarely been covered. The second is the effective use of BIM buildings' spatial information. There lacks the works or information aware of hybrid structure for BIM buildings indoor environment modeling. And the third is about the accuracy of the past result. The present related work cannot always guarantee the shortest past result. In this paper, a lightweight indoor path planning framework is designed for complex BIM building or considering the above aspects. As a web-based method, we describe our whole task as JPath from online and offline procedures corresponding to the operations or the front end and the server side. Meanwhile, due to the resource limitation, we seek to develop our lightweight approach in which as a large portion of the computation as possible is designed to be offline, or minimizing the resource consumption of the front end. As noted above, the complex building is composed of many interior spaces. By analyzing these spaces and their relationships, we firstly model the indoor environment with partitioned spaces, and then solve our path planning within these interior spaces as the divide and cork idea. It's also indicated that other procedure of
Now, John, you seem to have your video and audio seem to have stopped. Yeah, we can still see your presentation, but your video and audio seem to have stopped. Oh, we can hear you now. Just maybe if you want to stop your video and just try with just audio. I can't hear you now. Can you switch off your video and try just audio? I see you're speaking and I can't hear. Can you turn your mic on and off and just see if that fixes the problem?
Maybe he can leave the Zoom and then come back again.
Yeah, John, can you maybe if you want to quit Zoom and just come back, and if that doesn't work, then we'll play the backup video from this position.
This now is okay.
Yes, a little bit quiet, but yes, I can hear you.
Okay, okay. I just use my the video is stopped now. I just use.
Yeah, that's fine. You carry on then.
Okay, okay, okay. And as noted before, a complex building is composed of many interior spaces. By analyzing these spaces and their relationships of life, we first model the indoor environment with partition spaces, and then solve the path planning with these local spaces as a divide and cork idea. It's also indicated that the other procedure of path planning for the whole building is likely to be outlined and has been divided into a combination of M local solutions and space scale as equation 1, where the APPSSI stands for the indoor path planning in space SI. With these spaces, we can notice that some information for their path finding is stable, such as the space S0, S1, and S7, because these subpasses connect some stable portals except for the two with dynamic endpoints, for example, S5 and S2. More clearly, all these subparts, excluding the two dynamic ones, and can be the two ending parts can be prepared beforehand because they are stable in the building. And with this notion, it also represents that we can minimize the M in equation 1 to a constant value 2 in equation 2, where the S source and S target are the spaces containing source and target points. In this way, the BIM indoor path planning has been designed with a lightweight approach in which relatively few operations are online or the front end, while the others are offline with one-time perimeter sensing. Given the ending points, including source and target, only the online two out of MLPPS operations will be scheduled on the website. Meanwhile, the environment modeling and IPPS operations have been involved as our key operations. And we will introduce them in the following section. Based on the partition spaces, the whole BIM building can be modeled into a network structure with space and portal nodes, and the pipeline of our approach can be shown in figure 3. As can be seen, with environment modeling and path searching, we achieve our web-based lightweight indoor path planning through full online processing. In this section, we construct a network structure for indoor environment modeling in a top-down manner. It's organized from the building as the largest granularity, following story, space, and to grid cell as the smallest. The grid cell is generated as grid map for path refinement in one-time offline processing. Firstly, a cymatic guided story validation is implemented to parse and examine the building stories for abnormal cases. For example, the walls across two floors. In each story, considering the warm boundaries of interior spaces are almost sweeping results from their footprints. We propose a footprint analyzed space extraction based on image topological structure analysis. With this analysis, a hierarchy of the image boundaries is returned, corresponding with space boundaries. Meanwhile, a condition rule here from boundary closure is defined for space validation, and virtual boundaries is ended when the condition is met. In this condition, in this figure, we can see a virtual boundary C is ended between the point A and B for a logical space partition, and the space 1 is then partitioned into two smaller ones, named 1.1 and 1.2. For accurate pathfinding, a grid subdivision for the interior space floor is introduced to refine the floor map, in which the grid cells are evaluated with 1 or 0, depending on if it is occupied by any obstacle products. Observing the importance of the grid resolution, we investigate following empirical formula to calculate the grid resolution, where this table means the roundup operation. L star is the less estimation of the space range in major direction star, including X or Y. C stands for the number of obstacle products in crude space. A is the area of each cell, and lambda the empirical parameter. With the top-down manner, the indoor environment of the whole building has been gradually refined from building, story, space, and grid cells. However, their relationships yet have not been unified. We integrate them as a multi-layered network in which the layers are corresponding with the actual building stories. Between the layers, the vertical spaces and the next door spaces with similar structures are connected if there exists vertical stairs or horizontal portals. With this network, we can flexibly design and optimize the path searching. Based on our previous network structure, the main steps of our path searching optimization are network-guided global path selection and heuristics optimized local path searching. With the source and target position, we can firstly locate their corresponding spaces. For example, node 2 and 5 in this figure. And all the reachable paths that end with these two nodes can be accessed and selected from the network structure based on their path distance comparison. In this figure, we can see two reachable paths with color. Meanwhile, as we know, to complete the global path selection, the paths in space 2 and 5 plotted with red line should also be given with IPPS operation. And this is the primary all-line procedure. Moreover, we can observe that our global path selection can provide global guidance and dynamically avoid the path through the dangerous space. For example, the fire emergency in figure 6. The path does not go through the space 3, even though this path has a smaller distance. As for the IPPS operation, although the A-star algorithm returns the optimal path, it performs differently with the path direction, especially in the common cases that one of the ending cells in a narrow corner of interior space. In figure 7, we can notice that from the path searching area, and we mainly make two improvements for these situations in our heuristic optimized A-star algorithm. First, we employ a bidirectional heuristic search from the two ending cells. Second, we introduce a stochastic phase in neighbor cell selection where there are multiple best choices. We set a high selection rate, P, for choosing the cells, which is more consistent with the vector of the two ending cells at a low value of E of 1 minus P to support a further exploration for the smaller probability event. To evaluate our method, we implement our approach with a web-based server in C++ language and a front-end program in JavaScript for real-time local path searching. In offline indoor environment modeling, the experiment shows that all test state can automatically yield a natural network structure with the same setting as the corresponding references. Figure 8 shows that the time consumption of our method is less than the other two methods. Meanwhile, for the accuracy, with slightly higher efficiency than Zhou's method, our method can yield a shorter and a more precise path and has the similar accuracy with the standalone method. This is some visualization records from our experiments. Conclusion: this paper presents an approach for lightweight indoor path planning in complex BIM buildings, taking the mainstream building date format IFC as our input date. We design a lightweight pipeline to integrate the indoor environment modeling and path searching with separated online and offline procedures. The final experiment shows that our approach can reduce the online computational cost drastically and can dynamically search the shortest paths in complex BIM building. Meanwhile, there still exists limitations that need to be improved, such as the case of missing complex spaces on boundaries. In the future, we will enhance our method from these aspects. That's all for my presentation. Thank you very much.
Fantastic. Thank you very much for your presentation. We have, we're a little bit behind. I'm just going to take a question from the floor. I don't know whether anybody else has any questions. So from Liazu, she said, thank you for your presentation, Xiaojun. Could this technique be applied to non-playable characters in games, where, for example, the NPC tries to find the player?
In my opinion, our method is firstly, I think it's okay to use in the games, but our method, the part of our method focus on the buildings date. In our paper, we mentioned the IFC or BIM building, and some work are focused on the optimization for the BIM building date. But in the games, perhaps their building date are not same as this work. But
yeah, that's true. But I think she's more talking about the first part or the last part, which is not the optimization of the building, but finding the quickest path very quickly, because I guess in some games you're going to have the assassin chasing you or something and you're trying to get away.
Yes. The pipeline is pipeline is okay. It can be used. I think.
Yeah, it's very interesting.
Yeah.
I have a very quick question, and then we'll finish this session. So the other thing that I think when I was watching a presentation is you're not taking into account how the interior of the building is laid out once the building is built, right? So let's say that you've got, when people are dealing with space, open space is very easy to use. But once you start adding chairs and tables, then you start having obstructions. And maybe the best route which you would take is not necessarily your route if you were dealing with a fire, because those tables and chairs then get in the way and people say, I'm not going through that, I'm going to go the other way. Do you think you'd be able to add that kind of additional information in the future?
Yeah. Actually, some windows or other element, other virtual element in our practical case, we can also escape from the space, and we can use this, and the present work we will concentrate on is we use the other information like the main information we think is the width, like the window or other entrance or other entrance, especially the information, semantic information is not annotated with the door. Some building products we mentioned in products we mentioned it. Actually, it's a object in the graphics or some other area fields. We mentioned objects, but in BIM buildings, this field we mentioned with products.
Yeah. Okay. All right. Well, thank you very much. So